So in chapter 2, we're going to look at acids and bases. So some of this chapter will be review, being similar to some things that you may have covered in general chemistry. But at the same time, there will be a fair amount of new material as well as we start to talk about how these acid-base concepts apply to organic chemistry and why they're important from this perspective. So we will, of course, start with some review. And by that, we mean what is an acid and what is a base. And the answer to that question all depends on which definition we are using. So recall from general chemistry, you should have learned two primary definitions for acids and bases. You may also have learned about a third definition, the Arrhenius definition, but that's one that's not as helpful to us here because the Arrhenius definition mostly applies to things that are going on in water. With organic reactions, very few of them take place in water, and so the Arrhenius definition isn't as relevant to us. All right, but under the Bronsted-Lowry definition, we should recall that an acid is an H+ or a proton donor, and a base is a proton acceptor. And for most reactions, this is enough for us to think about in terms of what an acid is and what a base is. But there are cases where we have compounds that display acid-base behavior, but don't fall under this traditional definition of having protons to donate or accept protons. In addition, because this is a reaction that's taking place, it in a lot of ways makes more sense to think about what's going on in an acid-base reaction in terms of how the bonds are forming, which is based on electrons. So the Lewis definition, which is a bit more comprehensive, defines acids and bases in terms of electrons. So an acid is an electron pair acceptor, and a base is an electron pair donor. Now, what actually happens here is we end up finding out that anything that is a Bronsted-Lowry acid is also a Lewis acid. Anything that is a Bronsted-Lowry base is also a Lewis base. But the reverse doesn't work. There are examples of compounds that are Lewis acids, but are not Bronsted-Lowry acids. All right, so we should recall that for any generic acid-base reaction, we can take the acid HA plus water to form A- plus H3O plus. And so in this context, HA is our acid, and after it loses a proton, it forms A-, which becomes known as the conjugate base. Water here, because it's accepting a hydrogen, is our base, and after it's accepted a hydrogen, it becomes known as the conjugate acid. And then we use this generic equation, and this is all review from general chemistry, to come up with the equation that pKa is equal to the minus log of A- times H3O plus divided by HA. And recall that it's pKa that we use to define both acid strength, but we also are able to use it to define how strong of a base something is. So let's think about those terms. strong acid, strong base. So for a strong acid, HA is very willing to give up its proton. So the concentration of A minus and H3O plus are going to be a lot larger than HA. That means that our Ka value will be small. And since pKa is a negative log of this, the pKa value will be large. Now, given that pKa is a measurement of acid strength, how do we use it to measure base strength? Well, we know in an acid-base reaction that an acid and its conjugate base are in equilibrium. So if we have a strong acid, that is something that's very willing to give up its protons. So if a species is very willing to give up its protons, it's probably not going to want them back. And so a strong acid leads to a weak conjugate base. The inverse is also true. If we have a weak acid, that weak acid doesn't want to give up its protons, and therefore it's going to want them back, and we have a strong conjugate base. But these terms strong and weak are unfortunately not all that meaningful. And the reason I say that is, what would you consider to be a strong acid? Well, odds are in general chemistry, you probably had to memorize a bunch of strong acids, and they included things like HCl, HI, sulfuric acid, and so on. And so sulfuric acid, for example, has a pKa of -9. Hydrochloric acid has a pKa of -7. And so in general, we do consider those to be strong acids. However, it's all relative. And that's why sometimes, even though we use those terms all the time, strong acid, weak acid, they're not always the best terms to use. So here you can see another acid. And yes, this is actually the name of this compound. It's called magic acid. And you can see it's actually rather pricey. And yes, you are reading that correctly. That's $269 for 25 grams. So it has a cost of greater than $10 per gram. If you'd like some perspective on how expensive that is, here's the price of gold from November of 2019. And while you can see that that's higher than the cost of magic acid, it's not a lot more expensive than magic acid. But what's my point here? What is magic acid? Well, magic acid belongs to a class of compounds known as superacids. These molecules all have pKa's of less than -20. Remember, HCl had a pKa of -7. And given that this is the pKa, the p is negative log, this scale is logarithmic, that means that magic acid is more than 1 trillion times stronger than hydrochloric acid. So these are some examples of strong acids. Nitric acid might be something that we think of as a little bit weaker, pKa of 1.3. But we can also use this scale to measure pKa's of things that we wouldn't think of as acids, such as water, pKa of about 15.7. Much weaker than HCl, but much stronger than, say, hydrogen gas with a pKa of 35. Or you can even measure a pKa for methane. Hydrocarbons don't like to give up hydrogens at all. It has a pKa somewhere in the range of 55 to 60. So this scale is logarithmic, but it's a huge scale. As you can see, we can range from superacids of pKa of minus 25 to hydrocarbons, which can have pKa's upwards of 60. And the same thing is true for bases. So if we look at the conjugate bases here, HSO4 minus coming from a strong acid is a very weak base. Hydroxide, which comes from a weaker base, water, is a weaker acid water, is a stronger base. Now, when you took general chemistry, you probably learned that NaOH, or any sort of hydroxide, was a strong base. And in the context that you were in when you took general chemistry, this is correct. But this is due to something known as the leveling effect. The leveling effect basically says that if we have a base that's stronger than water, and we add it to water, that strong base will just react, get protonated, and form hydroxide. So under aqueous conditions, we don't really get anything stronger than hydroxide, because anything stronger than hydroxide just reacts with water. But in organic chemistry, we get organic solvents. And so things like ether, THF, or hydrocarbons are common solvents. And these allow for much stronger bases to be used. How strong? Well, imagine if we could remove this hydrogen. This one on the central carbon. Turns out that hydrogen is even harder to remove than the one in methane. And it would give us the following base. Well, how strong of a base is this? I mean, you've all worked with sodium hydroxide before, and you know that sodium hydroxide, while it is reactive, it's perfectly stable to have it sitting in a bottle on the shelf for days, weeks, months, years. This base, which is known as tert-butyllithium, let's see what happens with it.